Welcome back to lesson 4.4, the counting rule. In this lesson, we're going to learn about the fundamental counting rule. We're going to learn some about factorial notation, permutations, and combinations. And these are going to lead us to some of the formulas we're going to use in the next chapter. So the fundamental rule of counting is in a sequence of n events in which the first one has k1 possibilities, and the second event has k2 possibilities, and the third has k3 possibilities, and so forth. We can then just multiply those possibilities together. And we talked about that in the last lesson. I did an example where I kind of extended to this. So if you recall, we looked at finding the sample space of all the possible outcomes for the gender of a family having 3 children. And this is where I talked about this fundamental counting rule, which means that child number 1, there were 2 possibilities, and there were 2 possibilities for number 2, and there were 2 possibilities for number 3. And so there are 8 possibilities in the sample space. So how many possibilities are there if you have a 5-course meal where there are 2 soup choices, 3 salad choices, 4 vegetables, 5 main courses, and 6 desserts? So I'll let you pause and try this one on your own. So we have 2 times 3 times 4 times 5 times 6, which comes out to be 720 different meals that could be chosen. Seems crazy, doesn't it? Example 2 is I have 8 students in my class, and I pick one to read the opening lesson introduction each class period. How many or how big is my sample space from Monday through Friday if a student can be chosen more than once? So if they can be chosen more than once, I've got Monday, Tuesday, Wednesday, Thursday, and Friday. And that means if they can be chosen more than once, that each student could be chosen every day. So there should be 8 each of the 5 days, or 8 to the 5th. And if you put that in your calculator, that should be 32,768 ways that we could choose those students to read the open lesson introduction. Now, if I want to do the same thing, but if I'm saying a student can only be chosen once, then on the first day, on Monday, there's 8 students to choose from. But on Tuesday, the student that was chosen on Monday is no longer in my sample space. So there's only 7. And then on Wednesday, the first 2 students cannot be chosen. So there's only 6. And so on and so forth, all the way through Friday. And that means if they can only be chosen once, there's 6,720 ways that I can choose those students. So in probability and in some of our calculations, we're going to use something called the factorial notation. And factorial notation is where you use an exclamation mark. And the exclamation mark means that we're taking the n, whatever that number is, and we're going to multiply by n times n minus 1 times n minus 2 times n minus 3 until you get down to multiplied by 1. And you're going to figure out what that multiplication is. So if I were using 5 factorial, that really means 5 times 4 times 3 times 2 times 1. So in this case, that would be 120. If I had 0 factorial, that just means I have 1. So that's my value. If I had 7 factorial, that would be 7 times 6 times 5 times 4 times 3 times 2 times 1 is basically my 120 times 6 times 7. So that would be 42 times 120. And that would be 42 times 120. What did you get? 5,040. Now, permutations and combinations are two different ways that we can choose items. So just like we were choosing my students to read the introduction lesson introduction, the two different ways I had you do them were using permutations and combinations. You just didn't know it. So permutations are when the arrangement of n objects in a specific order using r objects at a time is called permutation. So I'm choosing objects and the order matters. So in a specific order. So order matters. Okay. So we're going to use this formula. NPR is how you pronounce it. It's the n factorial that we just learned divided by n minus r factorial. So if we wanted to do NP9, it's really n factorial over 10 minus 9 factorial, which is 10 times 9 times 8 times 7 times 6 times 5 times 4 times 3 times 2 times 1 all over 1 factorial, which is just 1. And so that comes out to be 3,628,800. 7p5 is 7 factorial over 7 minus 5 factorial. So that's 7 times 6 times 5 times 4 times 3 times 2 times 1 all over 7 minus 5 is 2 factorial, which is 2 times 1. And you can cross out the 2 and the 1. So we have 7 times 6 is 42 times 5 times 4 is 20 times 3 is 60. So 42 times 60 is 2,520. And 4 permutating 4 is going to be 4 factorial over 4 minus 4 factorial. So that's 4 times 3 times 2 times 1 over 0 factorial, which is just 1. So that's 4 times 3 is 12 times 2 is 24. Now we're going to look at combinations. Combinations are ordering of objects, but the order does not matter. So the number of combinations of R objects selected from n objects is denoted by n choosing R and is given by this formula. So order does not matter. Which means that ABC and ACB and CAB are all the same thing. So let's look at 9 choosing 6. So 9 choosing 6 would be 9 factorial over 9 minus 6 factorial times 6 factorial. Because we're also dividing out all of the repeats. That's the 6 factorial. So this is 9 times 8 times 7 times 6 times 5 times 4 times 3 times 2 times 1 all over 9 minus 6 factorial, which would be 3 times 2 times 1. And 6 factorial is 6 times 5 times 4 times 3 times 2 times 1. So we can cancel out the common factors. And then 3 goes into 9 3 times, and 2 goes into 8 4 times. So 3 times 4 is 12, times 7 is 84. Now, there is a way to do this in Desmos. And we're going to go to Desmos. And in Desmos, you can go to the menu. So the bottom left here, where we go to the menu, see where it says show keypad. So if I open that up, and then you're going to go to functions, and we're going to go all the way down. There's statistical functions we're going to use later. But if you go all the way down to, I always go past them, they're there. NPR and NCR, you can just use these. So we've already done the NPRs, but I'm going to do the NCR so you can see. So I'm going to do 7, 4, and that answer is 35. So 7 choosing 4 is 35. Let's look at example 4, or example 6, pardon me. So we're going to go back to sharing my example 6. The Foreign Language Club is showing a 4-movie marathon of subtitled movies. How many ways can they choose 4 movies from the 11 movies available? And it doesn't say that order matters. And so that means order does not matter. So we're going to do 11 choosing 4. So I'm going to go ahead and go back so you can use here. So 11 choosing 4, we're already doing that. So we can just go and change this to 11 choosing 4. So there's 330 ways that we could choose for the movies if order doesn't matter. And then if you look at example 7, it says we're doing the same thing, but now it says, what if they cared which order the movies were shown in? Then how many ways can they choose from 4 from 11? So that would be 11P4. So we are going to go back to functions and go all the way down and choose NP4. So that would be 11, choosing 4. And there's more ways because the order matters. So that's 7,920 ways that we could choose the order of 4 movies from 11 movies. And that is all for chapter 4. So meet me back in chapter 5, and we're going to use some of these things that we've learned about probability in chapter 5. Have a blessed day.